Great, yes. Good morning, welcome. As the title suggests, what we're going to be talking about today is the Vector API, a new feature that has been added to the Java platform. And so when I started putting the slides together for this, I thought, right, I shall put a slide together at the beginning and I'll talk about the Vector API before JDK 15. And of course, we had the Vector Collections class, which has been in there right from, I think, JDK 1.2 maybe. And so we can do various things with that. But of course, that is not what we're here to talk about today. So anybody thinks that we're going to be talking about the Vector Collection class? Okay, you're in the wrong room. Right. What we are going to be talking about is how we can use the new Vector API in terms of improving, potentially, the efficiency and the performance of our applications. But before we get into the API itself, it's worth spending some time talking about some of the background of how we're going to use the Vector API, and even more why we're going to use the Vector API. If you look at computer science, there is this idea of being able to do things concurrently and in parallel. But it's quite important to understand what is the difference between concurrent and parallel. And it's one of those questions I think is actually quite a good one if you're doing like an interview to ask your applicant, what is the difference between concurrent and parallel? Because people often get confused about this. And so let's spend a little bit of time talking about that. Concurrency. What do we mean by concurrency? Well, concurrency is where we have two or more tasks that start, run, and complete in an overlapping time period. But, importantly, there's no guarantee that they'll ever actually both be running at the same time. So at some point, they're both going to start, they're going to run and overlap in terms of the time, but there's no guarantee that at any point they will actually work together. If you think about the sort of older computers that we had, before multi-core, multi-CPU machines, we had single core, single CPU, but we could have concurrency. We could run a web browser at the same time as an editor or a word processor. And the reason we could do that is through a time-sharing operating system. We allow one application to run for a period of time, a quantum, and then we swap to another one, and then we swap back again. And by doing that very quickly, we give the illusion of more than one thing running at the same time. Even though they are concurrent, they're not actually running in parallel. They're not running at the same time. So concurrency, like I say, is all about having things that overlap in terms of time, but no guarantee they will actually run at the same time. Parallelism, however, is where you have two or more tasks that are running at the same time. That means that you actually need some way of doing more than one thing at the same time. And we'll get into the details of that as we go through. So if we look at concurrency again, we can have the idea of high-level concurrency. We could have two people working on two different computers at the same time, both doing a word processing document, and that is concurrency. They're both doing the same thing. It overlaps in terms of time, but again, no guarantee they'll actually be working on that thing at the same time. We can then start boiling that down into the machine level, and we can say, okay, let's introduce concurrency where we'll provide multiple CPUs. Again, as I said, with the time-sharing operating system, we don't have to have multiple CPUs. But this allows us to have both concurrent and parallel execution. We can do more than one thing at the same time. And then we can take that down to the next level, which is where we dig into the processor itself, and we start introducing multiple cores so that we can have both concurrency and parallelism in terms of operations at the processor level, and then we can share things like the cache to improve efficiency because we're able to get access to the data more quickly where we're sharing it amongst cores. So we can have single core, dual core, quad core machines, and so on. Now, if we look at the way that we approach concurrent programming in Java, there have been many attempts to improve the way that this works. Right from the very beginning, Java took a slightly different approach in that it introduced the idea of concurrency right from the very beginning. We had the thread class. You could instantiate a thread, you could provide a runnable interface object, and you could do something in a separate thread. If you look at languages like C and C++, you have to use external, or you certainly used to, you had to use external libraries to introduce that idea of concurrency. So Java had it right from the very beginning. Problem was that if you tried to do cooperating threads in Java, in JDK 1.0, quick show of hands, anybody here ever use JDK 1.0? Okay, I've got a few. Okay, good. So you will remember that if you wanted to use the thread class, you really only had 4 primitives that you could use. You had sleep, wait, notify, and interrupt. And that was how you had to write cooperating code. That was very low level, very difficult to get it right. So we introduced in JDK 5, I think it was, the idea of the concurrency utilities. Lots of higher level constructs, things like semaphores, mutexes, read-write locks, and so on. And that made our life simpler because now we didn't have to write all of that sort of code at a low level. We could use those directly as libraries, and it simplified, to some extent, the way that we wrote concurrent code. And in fact, Brian Gertz has written a whole book on how to use these things, which is an excellent read if you get a chance to read that. Then in JDK 7, we took another approach, which was looking at the idea of the fork join framework. The idea here was to say, well, okay, we've got a particular task that we can break up into subtasks. And ideally, we want to do that in a sort of like 50-50 split. So really what we're trying to do is split that task into 2. And then what we're going to do is we're going to do that recursively, break each of those subtasks into another set of subtasks, and then go on until we get to a unit which is small enough to execute in a single thread. What we'll then do is have the framework handle all of that for us. So we provide a way of breaking up the data. We provide the information about what needs to be done to the data in terms of processing it. But we let the framework handle all of this splitting up, allocating certain pieces of work to threads, having queues associated with it, the ability to do work stealing. So if one queue gets emptied, we can start pulling things from the bottom of another queue and so on. All of that's handled by the framework itself, which makes this kind of programming, again, simpler. We're using the framework, and it makes our life easier as developers. And then in JDK 8, we got streams and lambdas. This allowed us to take a stream of values from a collection and then process them in some way as a stream using the sort of typical filter, map, reduce approach, or something like that, where we'd have a certain number of intermediate operations, and then we'd have a terminal operation to gather everything together at the end. Great thing about that is that the library hides all of the complexity underneath in terms of how all this happens. And when it comes to making this concurrent, they introduced an extra sort of concept, which is actually really badly named, because they called it parallel stream. And it's not really a parallel stream, it's a concurrent stream. But that's what they called it a parallel stream, with the idea that you could break up your stream of values into certain divisions, and then you could have those handled by different threads. And it builds on top of the fork join framework from JDK 7. So we're using the same framework underneath just to say, take all of these values, break them up, and then handle them in parallel or concurrently, and then join them together. Now, there's a few things to talk about there. Firstly, don't assume that doing things concurrently is going to make things faster. This is a common sort of misconception when we start talking about both concurrent and parallel programming, is that we're going to get better results if we do things concurrently or in parallel. We don't even guarantee that we're going to do things more efficiently. And there are a couple of reasons for that. First is that certain operations don't decompose well into concurrent operations. Some do. So if we take things like sum, if we take min and max, these break up really nicely because if you're looking at, let's say, the maximum value, you divide your data set into 2, you can analyze each of those sets independently and get the maximum value from both of them. Then all you have to do is compare the maximum values from both of them and you get the result for what is the maximum of all of the data. And again, you can break that up into smaller and smaller chunks and get a set of maximum values for each of the chunks of data, do the analysis as you bring them back again, and end up with your maximum value. Same thing with minimum, same thing with addition. You can add things together independently. They don't relate to each other, don't rely on other pieces of data. However, some operations don't work well if you try and break them up and do them using something like a parallel stream, because sort is a good example. Sort is where you're dealing with the whole data set and you're trying to organize the whole data set in a particular way. So if you break the data set into two and you sort half of it and you sort the other half, when you join them together, there's no guarantee that that is going to be fully sorted for the whole data set. Now, there are algorithms like merge sort which will work in this particular case, but it's still not as efficient in terms of decomposing into these multiple sections of code to make it as efficient as possible. That means that when you're doing things like a stream and you want to try and make it a parallel stream, you need to think carefully about whether the operations you're doing really do work that way. Similarly, things where you involve I/O can be very problematic. If you're reading data from a file, the file is being read sequentially, so trying to turn that into a parallel set of operations becomes very difficult as well. You have to kind of do various tricks to try and feed the different threads independently, and it doesn't really work very well. So you don't get as good performance from that kind of thing. So like I say, concurrent programming in Java, we've tried all sorts of different things. Some of them work really well. It really comes down to picking the situation for what you're trying to do. So again, concurrent programming, you can use multiple execution units, CPUs, cores. Possibly it's going to improve performance. But again, when you're doing concurrent programming, you don't require those multiple units of execution. Okay, so let's kind of now move to the idea of vectors and what we call single instruction multiple data, because that's what we're going to use to do this. Now, again, a little bit of a sort of side here, which is, let's look at some vector mathematics. If we do simple addition of two vectors in mathematics, this is the kind of thing that we get. So here I've got a 3x1 matrix, I'm adding another 3x1 matrix, and the result is a 3x1 matrix. To do that, obviously, I add 4 to 3, I get 7, I add 3 to 5, I get 8, and I add 7 to 2, and I get 9. So this is all good. However, if we do matrix multiplication, mathematically, it's a little bit different. So I can take my 3x1 matrix on the left, and I can only multiply that by a 1x3 matrix. In order to do that, I can't do a 3x1 times a 3x1. I have to do a 3x1 times a 1x3. And rather than doing the individual multiplications and recording those as the results in another matrix, it's different in that here what I'm doing is I'm saying multiply 2 by 2, 3 by 3, and 4 by 4, and then add those results up. The result then is a scalar rather than a vector. The reason I'm talking about this is because this becomes significant when we get to the vector API, because the vector API works differently to vector mathematics. Single instruction, multiple data. This is where we get into the idea of truly parallel processing. Parallel is where we're doing a certain set of operations at the same time. So now what we have is the idea of our processor has a very wide register, or registers in it. Typically, if you're dealing with a 64-bit processor, you will have a number of 64-bit registers. For single instruction multiple data, we're going to have registers that are potentially much bigger than that. The idea being that we can store multiple values into that register at the same time. How many of those we can store is what we call the number of lanes associated with that register. Now, if we want to do some simple processing on a set of data, what we're going to do in terms of the way we code that typically is using iteration. So we'll take our array of values, and let's say we want to add 2 to each of those. So we'll do 10 plus 2 in the first iteration of the loop, we'll do 14 plus 2 in the second, 11 plus 2 in the third, and 8 plus 2 in the fourth. If we want to use single instruction multiple data, rather than doing that one at a time in the loop, what we'll do is use our very wide register, and we'll populate that with the values that we've got in our array, or as many that we can store in that very wide register. So here I've got enough space to store all 4 elements, so I have 10, 14, 11, and 8, obviously represented simply by bit patterns in that register. The important thing is that the processor, not only does it have these very wide registers, but it also has instructions built into it that understand that when it's processing that register, it's not treating it in the same way it would a single value. So if I say I want to add 2 to that, it's not just going to add 2 to all the bits across the register. What it's going to do is use the vector operation to say, I want to add 2 to each of the values in the lanes of that register, so that I'm repeating that operation across all 4 of them at the same time. So it is a truly parallel operation because I can add 2 to each of those values in one instruction cycle. I'm not adding 2 to the whole value across it. Each of them, I'm repeating the operation to those different values, and I get then a new set of values in my register that I can extract out. That's very efficient, obviously, because I'm doing 4 values in the space or time that I need to do 1 clock cycle. Rather than doing 4 different iterations through my loop, I do 1 iteration to process 4 values. Now, single instruction multiple data has been around for a long time. First introduced in 1966. And it's funny because if you look at a lot of the things in computing, we were having this discussion last night about this, and saying that, people think that they come up with a new idea, but chances are it's been implemented in either a language or a machine decades ago. And so single instruction multiple data, 1966. I'm going to guess that probably nobody can actually recognize what this machine is. Nope. Okay. It's an Iliac 4. I'd never heard of it either. And then there are other machines that became very popular in the 1970s, so there's the CDC Star 100 and the Texas Instruments ASC. I love computers like this because they occupy a whole room. You think that that's probably way less computing power than you have in your mobile phone right now. So it's always fun to see the way that things have evolved. Anyway, we had lots of machines that started using this because it was a very efficient way of doing numerically intensive operations. We then had a history associated with the instructions for being able to process single instruction multiple data. And so I won't go through all of this in detail, but you look back to the 1990s, HP introduced the PA RISC architecture that had some max instructions, quite small registers, so it was only dealing with 32 and 64-bit. Good old Sun Microsystems, who I used to work for, they introduced the UltraSpark processor that had the VIS instructions with 64-bit registers. And then Intel kind of got into the game back in sort of mid-90s, so the Pentium P5 had the MMX instructions, or multimedia extensions. The idea behind this was because people were trying to render graphics and video and things like that, so MMX was helpful because of the amount of calculations that needed to be done. Then they introduced with the Pentium 3 the SSE extensions to that. That's the streaming SIMD extension instructions, which went to a 128-bit register. Then in the Sandy Bridge architecture, they switched to the AVX instructions, 128-bit. Then Haswell in 2013 extended that to AVX2, 256-bit registers. And the current thing that we have is from the Xeon Phi processor, AVX 512 with 512-bit register. Right, let's get into the Vector API itself. What does this do? Right, so the first thing about this is it's what's called an incubator. And it holds the record for being the longest incubator that we've had since we started doing these kinds of things at JDK 10, I guess it was. And the idea behind this is that an incubator module is where we're creating an API that we want to include in Java, but we don't want to make it final straight away. The idea is that there is going to be feedback, there will be some decisions about things that might change, and we still have the possibility of changing it before we make it final. Normally it goes through sort of 1 or 2 revisions, but as I say, the Vector API is currently in the 6th incubator, and JDK 22 will make that the 7th incubator. Again, there was some discussion about this yesterday at the panel of the Oracle Java engineers, and the sort of general consensus was that this is going to have to wait for Valhalla to become more of a baked-in piece to the JDK itself before we get it final, because the Vector API is tied to the Valhalla project. You may have heard of Valhalla. It's to do with value types in Java. It's also connected to the Panama project, which is a replacement for JNI. So there's a lot of interdependency in terms of what the Vector API actually has to do. So we are at the 6th incubator, and that's what we're going to be talking about for the rest of the presentation. So the first thing, how do we represent vectors in Java? So let's take an example where we have a machine, fairly modern, which has an AVX2 instruction set, and it has some registers which are 256 bits wide. To represent that, we will use the very imaginatively named vector class. And it's a vector which has a type parameter e to represent what it is we're going to store in that vector. Because remember, all we've got there is a register with a certain number of bits. To make it have more meaning, we then define that we have a vector of a specific type. And we'll call it a vector of integer. Now, the thing about Java is because it is object-oriented, but we have primitive types. So we can't have a vector yet, because that's Valhalla that will introduce this. We can't have a vector of int with primitives, so we have to use the wrapper class. Now, technically, we're not doing any boxing and unboxing, so it's not an overhead in terms of performance. It's just that we have to represent the type as a real Java type rather than a primitive. But don't worry about it actually doing boxing and unboxing to these object representations. Realistically, what's happening is just using the primitives underneath. So we can put a certain number of ints in that register. Int is 32 bits wide, so we can put 8 of those into our register. And those are our lanes. So remember, these are where we have separate values in the register itself. If you look at the vector, it includes a certain number of methods which are common operations across all vector types. So things like add, subtract, divide, multiply, minimum, maximum applies to all types of vectors. No matter what you're storing in there, you can add them, you can multiply them, you can find the minimum, and so on. What you then have are concrete subclasses of those which represent the type-specific ones. So you take your vector of type E, and then you can create a subclass of that, which is byte vector, short vector, int vector, which is a little bit annoying. And some of the naming on this I find a little bit annoying because, you know, they called it int vector because int is the primitive, but we know that the type is integer. So wouldn't it have been better to call it integer vector? But it's a small thing. Long vector, float vector, double vector. And each of these classes will also include methods which are type-specific. Now, that will actually include things like from array, because when you're trying to populate a vector, you need a from array with the type-specific, primitive-specific array information. So going back to our idea of vectors, like I said, we have the vector of type E, then we have the vector of type integer, which represents what we're going to store in that vector. And then we have, again, the really badly named vector shape. It's not a shape, it's a size. It is how many bits there are in the register. So why did they call it shape? Shape is it's a geometric thing. It has vertices, it has lines. I suppose technically you could say it's a rectangle, but it's not really a good definition there. So really what we're dealing with is the size. And we'll see that, obviously, in this case, we have a 256-bit wide register, so the vector shape is S underscore 256 underscore bit. We can't start a name with a number, so we have to put an S in front. And there are different vector shapes, as you would expect. So we have 64, 128, 256, and 512-bit explicit sizes for our registers. But we also have this other one, which is S max bit. And again, why did they lowercase, or why did they camel case that? So talking a little bit more about the S max bit, This is a good way of going cross-platform, because if you want to run your application on different machines, which potentially have different microarchitectures with different width registers, then rather than hard coding into your code the size of the register, you use smaxbit and it will give you whatever is the maximum size of the register available on that particular platform. A couple of other things to note about that. One is that if you look at the Intel processors, they can actually have multiple shapes or sizes. So you can have, 128-bit and a 256-bit register, and you can use those independently. If you look at ARM processors, you have to use the smax bit as the way of referencing the very wide register there, because they can be anywhere from 128 to 2048, so they're a very wide register. But it is vendor specific, so it depends on whether you're using like Apple Silicon or whether you're using a Snapdragon processor or whatever, as to which of the registers they've decided to implement in the actual packaging. So with the ARM, only supports one shape, but you use the smax bit to reference whatever's available. You then have the idea of a vector species. And the vector species is represented by the vector species of type E class. And it's really a combination of, well, two things, but it gives you three pieces of information. First is the element type, and the second is the shape or size. And so if we look at what you always get in terms of when you print the value of a species, you will see species, and then you'll get the E type, the V length, and the shape. And as an example, what you'll see is int to indicate that we're storing ints in our species, in our vector. 8 is the number of elements that you can store in that vector. And S256-bit is the width in terms of bits, so the shape of the vector. So it gives us a way of understanding the kind of combination of information about the vectors we're going to be using. Now, if we want to use a species, we will need that. So what we could do is something like this. So we'll go, okay, vector species of type integer, we'll call it int species, and we'll create a new int vector, which is a species with a 256-bit wide register. So that includes the information, which is that we're now storing ints. We have 8 of those that will fit into a 256-bit register, and the size of the register is 256 bits. What we can then do is use that to determine how to effectively use the registers within a loop. And this is where, as I say, if we use a species which is of the maximum number of bits, this code will allow us to switch between different size registers without having to change our code. So there are two things that we can get from that. First is what we call the vector loop size. And that's essentially the striding that we're going to use when we loop through the data that we've got in our arrays. Essentially, that is the number of elements that we're going to be able to store into our register. So that's going to be 8 in the case of the example that we're using here. And then we've also got the, sorry, that's not, no, that's the length, isn't it? Yes. So the length is the number of lanes, so 8. And then the loop bound basically says take the number of elements in our array and figure out how many iterations we need in our loop to move through all of those when we're using a stride of 8. So it's essentially just dividing the length of the array by the size of the register. But we have a method to do that, so it makes it more portable and more easy to use. So we use that, and then we have our loop where we say, okay, loop through the array, use the vector loop size to indicate how many iterations we'll have, use the number of lanes as our stride that we're going to move through, and then we create vectors from that, saying, okay, we'll create an int vector using the int vector from array method, pass in the species, so it understands what we're using in terms of the vector, pass in the name of the array, and then also pass in the index to the array so that we can start populating from that point. And then as we move through, we'll take new values. Do the same with array B, and then do some sort of processing. So this allows us to simply say, okay, create a loop to go through the array, do it in chunks that will fit into the vectors that we're going to use. We then have the idea of a vector mask. And there's a couple of uses for vector masks. The first is that if you think about it, you may have an array which is not an integral multiple of the number of lanes in your vector. So if you've got a number of lanes of 8, and you've only got, let's say, here we've got 30 elements in my example. So you've got 30 elements and a number of lanes of 8. That doesn't divide evenly into there. You'll have 3 of 8, plus you'll have one set of 6 that you need to process at the end. So you can use a mask to say, when I get to the end of my array, rather than populating it with all 8 elements, I'll populate it with however many I've got, which is 6, and then I'll just mask out the last 2 so that I'm not getting any confusion in terms of the operations that are applied to that. If you're doing something like a simple addition, that doesn't really matter, but when you're doing things like division, for example, or minimums and maximums, it can be more significant. So you can mask out the lanes that you don't need for the operation so that you can still have use of the vector when you don't have a complete set of values to fill the vector with. And so just quoting directly from the spec here, it says, an operation suppressed by a mask will never cause an exception or side effect of any sort, even if the underlying scalar operator can potentially do so. So it protects you completely from any effect that might have by masking out the operation. If we want to use the vector mask, taking the same loop example we had on the previous slide, here what we're doing is simply going through our set of data, using the striding as the number of lanes, repeating for the vector loop size. But if we want to use the mask, all we do is introduce a vector mask of type integer, and we create that from the int species, and then we get index in range, and we pass in the current index and the length of the array. So it will calculate how many bits to mask out based on the end of that array. So it's the simple way to do that. And then we can simply pass in the mask to the operation when we create the array, create the vector from the array, and we'll use the mask to handle that for us. So it's very simple to use the vector mask in that particular instance. But there's another case where we can use a vector mask, which is where we want to do conditional execution. In this case, what we're saying is, let's not use all the values from a particular vector, because we want to decide that only certain ones are going to be actually used. So we'll create some mask that says, right, we want to combine 2 vectors, but do it in such a way that we only take certain elements from the first one and certain elements from the second one. And we can determine that by the mask. So for example, we could create a mask which is sort of 0, 1, 0, 1, 0, 1, 0, 1, and that will say, take half of the elements from the first vector, half of the elements from the second sector, and do it in such a way that we're alternating between those elements. So if we set the mask in the so if we set the bit in the mask, then the value will come from the second vector, and if we unset the bit in the mask, then it comes from the original vector. So it's just false basically means take it from the first one, true, take it from the second one. And we can use this method called blend, which will blend 2 vectors using that particular mask. Again, fairly straightforward, but allows us more flexibility in terms of what we're going to be able to do. We can also shuffle vectors. And again, this gives the ability to take a set of values and then reorder them in a way that we want to do specifically. So the example I've got here is, let's say we've got 8 values in our vector. What we actually want to do is take our 8 values, and then we want to interleave them into a new vector, but we'll do it such that the second half, so represented here, is actually interleaved with the first value of that second half as the first value of the new vector. So by specifying the order of the indices here, so 1, 3, 5, 7, we'll take the second half of the values, and then 0, 2, 4, 6, we'll take the first half of the values, and we can interleave those using that way of doing the shuffle. So we pass that into the vector shuffle, create it for an int species, and then we just call the rearrange method with that shuffle, and it will do it for us. Vector operations. So once we've got our vectors, what can we actually do with them? Well, we've seen a couple of things already, like shuffling and blending and things like that. But there are a very wide range of operators that we can use. So it gives us a lot of flexibility in terms of what we can do when we're using vectors. So there are also sorts of different types of operators which are represented by the vector operator class. And so you can see there's associative, where we don't care about the order of things. Add and are associative, so we don't care. Binary, where we've got two different parameters that we're going to take. So we want to say, okay, we want to divide this vector by another value, take it to the power of something. We can do comparisons, looking for equality, less than. Actually, there is a greater than. I found it this morning, so ignore what I say there. Conversion, we can do double to byte, byte to float, float to double, and many, many combinations of those. Ternary operators are where you get three values, and there's a specific thing, there's one of those, which is FMA, which is fused, multiply, and add. And that is a very common operation that people like to do, so you can do it as a single operation using FMA. Test, you can do for things like is finite, is negative, and then unary is where you've got one argument because you want to take the log of a value or the negation of the value or the not in terms of binary. If you look at vector operators, you will see a whole range of different things that you can use there. So if we want to use that, we can do really what we like. And so here's a simple example where we're doing some mathematical operations. We want to calculate the hypotenuse based on Pythagoras. So we've got two values for a and b. So we're doing a squared plus b squared equals c squared. In terms of using that with vectors, what we can do is populate the float values into our first vector for the a values, populate the b values into a second vector, and then we create a third vector, which is the result, by calling va.multiply by va squared. Then we add vb multiplied by vb, b squared, and then we take the square root of the result, and that gives us our result for the length of the hypotenuse. So again, really it's up to us what we want to do in terms of making things as simple or as complicated as we like. We can also do reduction operations. Rather than taking a set of values and then applying the same operation to each of those values in a single clock cycle, what we can also do is say, well, we've got a set of values, I want to take all of those values and reduce it to a single value. Something like where we want to add all the values. So we're creating a sum of what we've got in our array. To do that, we can use the reduce lanes method, which obviously will reduce our lanes into a single value, and we'll pass in an operator, in this case add, to say we want to add everything up, and we'll also pass in a mask in case we have values that we don't want to include in the operation. And that will then produce a sum. We can then continually do that for all of the values in our array and create an average from that. How well does it work? Okay, so this is kind of the interesting bit, is if you look at what results do we get if we start using the vector API versus not using the vector API. So SIMD is fast, yes, but there are many other things that come into play. First of all, you have to remember that main memory access is slow compared to like register access, for example. And if you look at the way that the CPU caches things, you have, in some processes, you'll have an L1, an L2, and an L3 cache. And that is basically based on the speed and the locality of the cache. How quickly you can get data from that, if you took it to the L1 cache, typically somewhere in the region of 3 to 5 cycles, clock cycles. L2 cache is going to be somewhere 8 to 20, L3 is going to be 50 to 80, and then RAM, if you're going out to main memory, is going to be sort of 100 plus cycles. That means that if you're doing vector operations and you have to go out to RAM a lot, the benefit you'll get from doing 8 or more operations in parallel will be vastly swamped by the time you're waiting to get the data to actually process it. The further you go for the data, then the less improvement you're going to see by using the vector API because of the SIMD effect. So realistically, you want to keep your data as close as possible and as much in cache. The other thing is that the JIT compiler actually already knows about single instruction multiple data. And so it can take advantage of that in many situations. What you'll find is that the code that's generated by the compiler, the JIT compiler, will be, in many situations, identical or even better than what you get with Vector API, which sort of starts you thinking, well, why do we need the Vector API? But we'll see why we need that a little bit later on. If you really want to see the difference, what you need to do is turn off the compiler's ability to use single instruction multiple data or auto-vectorization, and you can do that with the -XX -use superword option on the compiler, or no, actually command line for the VM, because it's the JIT compiler. Now, I'm going to show you some results which I've borrowed from Thomas Zeltzer, who wrote a very good couple of articles about this. And so I've just used his graphs, so I'm giving full saying that he was the one who produced these in the first place. So what he did was he looked at, okay, let's take two vectors and simply add the two together. And he did that for analyzing different sizes of arrays. And he got these results when he had the idea of using auto-vectorization, so the compiler could do whatever it wanted to. And what he saw here was that most of the time, the results were pretty much the same as you would get using the Vector API. So the red line is Vector API, blue line is just the JIT doing its work. But a couple of things that sort of stuck out here. One was for a small set of data, 64 elements in the array, the Vector API outperformed quite significantly. And it turned out that in that case, the JIT compiler was making some decisions about how to do things to optimize for older architectures, because it just decided that with a small set of data, it would do this. So it was really using a smaller vector operation rather than the explicit one that you can use in your code. So it came out with better performance for the Vector API. And it also turned out that with 32,000 elements, the Vector API performed noticeably worse. And that, again, was because of what the JIT compiler was doing wasn't just using vector operations, it was doing more loop unrolling, which is another technique for improving the efficiency of your code. It was doing much more loop unrolling in that particular case, which gave it an advantage over just the pure Vector API. If you take out the auto-vectorization, then it becomes a lot more apparent as the difference between what you would get without using vectors and what you get using vectors. And the shape of this graph is exactly what you would expect, because you get a peak with about 512 elements in your array, then that performance benefit will start dropping off because of the fact that you're going further and further to get your data. So you're hitting the L2 cache, L3 cache, and then ultimately going out to the RAM. So by the time you get up to sort of millions of elements in your array, the time it takes to access the data swamps the ability to use the Vector API to get more advantage. Taking the idea of statistics as well, this is where things get kind of interesting, because what we can do here is analyze an array and look for two arrays and say, let's count how many elements in the first array are less than the second, how many are equal, and how many are greater than the second vector or second array. And we can do that using the operators we've got in our vectors, so less than, equal to, and greater than. And because we're operating on a number of different values, we can also get the number of things that match that by calling the true count method to get how many actually were less than, equal to, or greater than. If we look at the results from that, even using the auto-vectorization, we get very, very different results between the standard JIT compiler and the Vector API. And this is as a result of the fact that in situations like this, the compiler will not be able to recognize that it can auto-vectorize that. So here, if we take that as a simpler example, and we say, let's take two arrays, and we'll only add the element of the second array to the first array if it is even. So we're introducing a conditional, a branch statement in that. If we look at the code that's generated by the hotspot C2 JIT compiler, we'll see something like this. Now, we don't need to go into all the detail about this, but essentially, it's not using vectorization. So it's not doing auto-vectorization of this, and the only advantage you're getting from that is it's doing loop unrolling of 2 elements per iteration. So it's because of that branch statement, it's not able to recognize it as auto-vectorization. However, since I work for Azul, I'm going to plug something that we do, which is we have different JVM called Platform Prime, used to be called Zing. Anybody heard of Zing? Okay, a few people. And that uses a different JIT compiler. So we use what we call Falcon, and it's based on another open source project called LLVM. If we look at the code that's generated for that same set of instructions there, then we see that we're getting vectorization, so auto-vectorization from the JIT compiler, and we're also getting loop unrolling of 4 elements per loop, plus the 8 that we're being able to do with the very wide register. So the ideal would be that the JIT compiler would recognize this for us, do the auto-vectorization, and so we wouldn't have to use the vector API. But in situations where you get things like branches, then if you're using Hotspot, this is something where you can benefit from using the vector API. Just to summarize, conclusions, basically vector API allows you to do explicit single instruction, multiple data processing. Simple situations may not necessarily benefit. So if you're using small sets of data, simple operations, you're probably not going to get much benefit from using it because of the auto-vectorization in the JIT. But where you've got more complex things, where you do have branches, for example, then where the JIT compiler can't recognize that for auto-vectorization, you will get substantial benefits. Again, benefits are reduced as the size of the data increases because of the fact that you've got the overhead of the latency of access. And ideally, like I say, the compiler would auto-vectorize for all of your code. Azul Java, since I work for Azul, like I said, we have Platform Prime, which is our improved performance JVM, and we also have Platform Core, which is our straight builds of OpenJDK. And since I've just about run out of time, I guess I may have time for one question, perhaps? Okay, so anybody got a question?
Even if you don't get a performance gain, do you get any energy savings using CPU?
I guess that would be true, yes. So the question is, even if you don't get performance gains, would you get energy savings from using the vector API? I think it would depend to some extent on how much the JIT compiler can do the same thing. Because if the JIT compiler is also generating vector code, then there really isn't any difference between both the performance and also the energy saving, because it's effectively doing the same thing. It's only where you really get a difference between what the JIT compiler generates and what the vector API generates, where you would see both a performance impact and an energy saving. Yep.
If you have a virtualized platform, then the virtualized CPU that you have is not necessarily one-to-one mappable on the actual CPU.
Right, so the question is, if you're using a virtualized environment, is the virtualized CPU may not be a one-to-one mapping to the real CPU? I don't know. I've never seen a situation where the virtualization actually changes the... I don't know. I don't know the answer to that. I'm going to be honest and say I do not know the answer to that, because I haven't come across a situation where virtualization has actually changed the way the processor looks from the virtualized environment point of view. So no, I don't know the answer to that. I've got one more question, if anybody has one. Or not. Oh, no, right, yeah.
Something that I would like to try is it possible to calculate a matter what set using vector API?
Absolutely, yes, because you've simply got a set of values and you're applying an operation to all of those values, then yes, you could write that code in the vector API very easily. So yes, a Mandelbrot set would be an interesting thing to do. Yeah, I'm sure try that myself, actually. Okay, so I think we are now officially out of time, so thank you very much.